Hello, today I'm gonna do chemistry because I have a chemistry test investigation next week. So it's gonna be on gas laws. Okay, so this question is basically like a shortened scenario kind of thing. So part A, um, part A, so first question. Okay, let me read the actual scenario first. So basically, a student is investigating the relationship between the temperature of a gas and its volume. They trap a sample of atmospheric gas inside a sealed 50 milliliter glass gas syringe. The plunger of the syringe is free to move. The student completely submerges the gas syringe in a water bath. They heat the water bath using a hot plate and record the volume of the trapped air at 5 different temperatures. The atmospheric pressure in the laboratory is recorded as a constant at 101.3 kilopascals. And there's some experimental data with 5 trials, the temperature of the water bath, and the volume of the trapped air. And part A, 1, asks identify the independent variable and the dependent variable in the investigation. So obviously they're trying to record the volume of the trapped air. So that's definitely the dependent, since they're recording that, so they don't know what it is, so it must be dependent on some other variable they're changing every single trial, which is the temperature of the water bath. So the independent variable is the temperature of the water bath, and the dependent variable is the volume air. Okay. Part 2 says, a student wants to plot the data to prove the specific gas laws and extrapolate the graph to find the value of absolute zero. Say the exact variable and unit that must go on the x-axis and what variable must go on the y-axis to achieve the linear graph that can be extrapolated. So the graph should look like this, and then that's the positive, that's a negative, and then we extrapolate to negative 273 or like that, and there's 0 kelvins, but we don't know what Kelvin is, what absolute zero is, so they want to find absolute zero in units of degrees Celsius. This makes it so that because volume can't go negative, it must be temperature on the x and volume on the y. So volume of trapped air in milliliters go on the y-axis, while the temperature of water bath degrees Celsius go on the x-axis. Okay, and that's for part A. So part B asks, as the water bath is heated from 10 degrees to 90 degrees, the volume of the syringe expands. I just sneeze so hard. Oh my gosh, I'm kind of sick. Okay, you can hear me. Hopefully you can hear me. Okay. Can you hear me? Oh well. As the water bath is heated from 10 degrees to 90 degrees, the volume of the syringe expands, assuming the external atmospheric pressure pushing the plunger remains strictly constant. Use the postulates of the kinetic molecular theory to explain why the volume of the gas must increase as the temperature increases. Okay. So according to the kinetic molecular theory, as the temperature increase, the kinetic energy of each air particle in the syringe increase as the pressure is kept constant and the particles only collide with each other and the each other and the walls of the container as the particles they collide with each other perfectly elastically, the extra kinetic energy must be put into colliding with the syringe, pushing it outwards and increasing volume. Yep, that should be good. And for part C, it says to assume the air inside the syringe behaves in an ideal gas, use the data exclusive from trial 2 to calculate the exact numbers of moles of air trapped inside the syringe. So it's just using the PV equals nRT formula, and we know that pressure is 101. Wait, what is it? 101.3 kilopascals. Volume equals to trial 2. It's 33.4 milliliters equals 0.0334 liters, and T equals 30 degrees, which equals 273.15 we're using. Should be 15 plus 30, which equals to it should equal to 303.15 degrees, and R is a constant, and the constant is 8.314. I think it'll be equal to, oh well, whatever, that's just a constant. So that means N equals PV over RT, which equals to, I think that's sufficient working out. I'm just gonna put in a calculator. PV, so 101.3 plus, times 0.0334 divided by 8.314 divided by 303.15. That should equal to 303.15 equals to 0.00134424, which equals to 1.34 times 10 to the power of 123 moles. Yep, that should be good for part C. And part D, I'm gonna sneeze. Okay, part D. Part D says the students realized they forgot to lubricate the glass plunger before sealing the syringe. As a result, there is a significant physical friction between the glass plunger and the walls of the syringe as it tries to expand outwards. Does the friction represent a random error or systematic error? Justify your answer. So part 1 is definitely systematic error, as the error is constant in each trial. And for the second question, it says explain exactly how the friction will affect the volume reading recorded in the data table. So basically what happens is the friction will oppose the expand in volume of the air particles, so the volume expanded recorded will be actually smaller than the actual value it should have expanded. So we're just gonna write that. So the friction opposes the expanding volume of the air particles, making the recorded data smaller in volume than the actual data. Oh well, that should be good. And for part E, it just says a second student decides to repeat the investigation. However, instead of movable glass syringe, they trap air inside a rigid sealed steel cylinder. What? Inside a rigidly sealed steel cylinder equipped with a pressure gauge. They place a steel cylinder in water bath and heat it. The fact which specific gas law in this new investigation is testing is the mathematical formula for this law. So basically what's happening is because the last experiment they kept the pressure the same, but this time the pressure needs to change, but the volume is the same. So we find the relationship between volume and temperature, and we know that is the Gay-Lussac's law. So just gonna write that. So they are testing the Gay-Lussac's law with volume kept constant and finding the relationship between pressure and temperature. Formula is P1 over T1 equals P2 over T2. Oh well, that's it for this gas laws. Hopefully I do good next week. Alright, bye bye.